Hello everyone, welcome back to our math channel. Today we're going to start with some awesome math. So we have two equilateral triangles talking to each other, and one asks the other, "Why are circles so hot?" And the other one responded, "Because they're 360 degrees. Hi everyone, my name is Cytlaly Rodriguez and welcome back to Chapter 11, Transformation, Symmetries, and Tiling. Let's start with question number 1. We are asked to reflect the pattern block figure. Ephraim and Devontae are asked to reflect the figure on the left. They are asked to reflect it, although it does look like the figure on the right. They didn't reflect it on the horizontal line. They turned it, it looks like 90 degrees, where it's in rotational clockwise instead of reflecting over the line of reflection, the horizontal line, which is called the line of reflection. You reflect it in the middle of each square. When you do that, it's like a mirror image. The figure literally just flips, making the triangles go to the bottom, the square staying in the middle, and the trapezoid at the very top, like the image on the right. The figure on the left are called objects, and once it's reflected, it's the image on the right. And he should have reflected it instead of rotating it. Well, they should have. Number 2 asks us to demonstrate one line of symmetry. This semicircle has one line of symmetry vertically, because if we fold it in half, we can see that each side matches. Number 2, an isosceles triangle. This has one line of symmetry going vertically, because if we fold it in half again, it's one line of symmetry. It matches. Number 3, we have a slanted isosceles triangle, which has one line of symmetry going horizontally. Continuing, we have a square. A square has one line of symmetry going in the middle. If you use your imaginations, it can be actually two rectangles equaling one square. Then we have a hexagon, which has one line of symmetry as well. This one can actually have more than one, but it has no rotational. And the rhombus has one line of symmetry going horizontally, and if we fold it in half, it matches exactly. It also can be two, but no rotational. If you use your imagination again, you have two triangles equaling one rhombus. Number 3, Myra is asked, number 2B. We are asked to find rotational symmetry but no reflection. Number 1, we are given the square. The 180 degrees is what the original shape should look like. If we rotate it 90 degrees, this is what the shape would look like then. Number 2, we are asked to find the rotational symmetry as well with no reflection. Once again, the rhombus is 180 degrees. If we flip it 90 degrees, this is what it would look like. The third figure, we are given this shape, which is 180 degrees, and if we flipped it 90 degrees, this is what the shape would look like. There are 4 rotational symmetries that have no reflection. This is the last one. This shape is 180 degrees. If we were to rotate it 90 degrees, this is what the shape would look like. To C, we are asked to find and demonstrate one line of symmetry that has rotational symmetry. This shape on the left has no rotational symmetry and no line of symmetry. How I know this is if we flip it, if we fold it horizontally or vertically, the sides do not match. Therefore, it has no line of symmetry. No line of symmetry equals no rotation. The rhombus has two lines of symmetry. If we fold it in half, it matches a big square. If we fold it the other half, it matches a big square. Horizontal or vertically, the sides match. Since it has two lines of symmetry, it has a rotation. The isosceles triangle has a line of symmetry and rotation. This square has two lines of symmetry and rotational. The isosceles triangle slanted has one line of symmetry, and the semicircle also has one line of symmetry. And so does the shapes up above here. They have no line of symmetry as well. Here, Myra is asked to cut out a regular pentagon, a hexagon, and an octagon, and to find the vertex figures. We know that the center of these shapes have to equal 360 degrees. So we know that the pentagon is 108 degrees because we use the formula n minus 2 times 180 divided by 5 equals 108. We just substitute the number of n equaling the number of sides. So 5 minus 2 times 180 divided by 5 equals 108. The octagon, it's 135 degrees, which is 8 minus 2 times 180 divided by 8 gives us 135. The hexagon, is 120 degrees. How I know this is 6 minus 2 times 180 divided by 6 gives us 120. Once again, to figure out the degrees of the hexagon and the pentagon and the octagon, we use the formula n minus 2 times 180 divided by n, where n equals the number of sides. If we add up 108, 135, and 120, we get 363 degrees, which is incorrect. We are to find where Myra messed up. She messed up where the corners are touching each other. The angles, the sides are touching each other. In order to make it 360 instead of 363, we add this gap between the pentagon and the hexagon. We do 363 minus 3-degree gap gives us 360. For A, we're asked if triangle QPT is congruent to triangle SPT. How we know this, if we look at the intersecting line, the principal intersecting line of P and T, we see QPT. If you look at it, it's one big triangle. If we look at this side, PST, it's also one big triangle. That means that all the sides have to be congruent to each other and have to match. In order for it to match, they have to be touching this intersecting line of P and T. Is angle QPT congruent to angle SPT? Angle S is congruent to angle Q. If we look at this, they have the same angles. Also, they have the same angles as P and T. All these angles are all the same. Therefore, they're congruent. Why is triangle QPV congruent to triangle SPV? Let me tell you why. It's because of the rule of the side angle side. What does side angle side mean? That means exactly what it says, that the sides are equal and the angles are equal to each other. That means they have to be the same degrees, the same length to be able to be congruent. Triangle QPV is congruent because QPV is congruent to PSV, making it two small triangles touching the same intersecting lines. Why is angle QPV a right angle? QPV is adjacent to SPV. This is why this makes it a right angle. They're right here touching at the right angle, making it 90 degrees. (5A), we are asked to create a regular pentagon. We're given a circle and label it penta. Here's the pentagon, and we labeled it penta, like it said on each vertex, which is the yellow dots. Here we're asked to construct an equilateral triangle in a circle, and we labeled it PQR. Now we are to inscribe penta and PQR, which is put all together, and label it and find the lines, match every single line together. Then we are asked to find what the angle of NOQ is. We know that the circle is 360 degrees. If we split that into equilateral triangles, we get 5. So we do the equation of 360 divided by 5, which gives us 72 degrees. That's the whole circle we're talking about. So therefore, the center of the pentagon is 144 degrees. To find the angle NOQ, we do 144 minus 120, giving us 24 degrees for angle NOQ. 6A, Jenny is asked to hold a ruler 2 feet in front of her eyes and illustrate a figure. Here's the figure. So where she's holding the ruler, if you look at it, it's a small equilateral triangle. We're labeling it A, B, C. As it reflects back, we can see it's a bigger triangle, but it's similar shapes, and we label that D, F, E. So we know that angle A is congruent to angle D, which is here, which is the bigger one, and angle B is congruent to angle F, and angle C is congruent to angle E, which means they're identical, they match, and this is what it would look like. 6B, we are asked to demonstrate how Jenny can measure the height of the cliff with equivalence ratios in similar triangles. So what does that mean? Since we already have this label, we know that it's already given to us that 1 mile equals 5,280 feet. We do 5,280 divided by 4 because we get 1,320. To convert 1.5 inches, which is the lines that mark separate by the ruler, to convert that into a decimal, we do 1.25. So we have 2 divided by 1,320, giving us 0.125 for the cliff, the height of the cliff, divided by the height of the cliff. To find out what the cliff is, we have to use the formula. 1.125 times 1,320, which is up here, and we divide it by 2 because it's 2 shapes, we get 82.5 feet. Thank you everyone for watching this today, and I hope you learned something.